Section 1.3, Thermal Expansion. Learning Objectives. By the end of this section, you will be able to 1. Answer qualitative questions about the effects of thermal expansion. 2. Solve problems involving thermal expansion, including those involving thermal stress. The expansion of alcohol in a thermometer is one of many commonly encountered examples of thermal expansion, which is the change in size or volume of a given system as its temperature changes. The most visible example is the expansion of hot air. When air is heated, it expands and becomes less dense than the surrounding air, which then exerts an upward force on the hot air and makes steam and smoke rise, hot air balloons float, and so forth. The same behavior happens in all liquids and gases, driving natural heat transfer upward in homes, oceans, and weather systems, as we will discuss in an upcoming section. Solids also undergo thermal expansion. Railroad tracks and bridges, for example, have expansion joints to allow them to freely expand and contract with temperature changes, as shown in Figure 1.5. Figure 1.5. A. Thermal expansion joints like these in the B. Auckland Harbour Bridge in New Zealand allow bridges to change length without buckling. Credit. Modification of works by SJU, Wikimedia Commons. What is the underlying cause of thermal expansion? As previously mentioned, an increase in temperature means an increase in the kinetic energy of individual atoms. In a solid, unlike in a gas, the molecules are held in place by forces from neighboring molecules, as we saw in oscillations. http://cnx.org/content/m58360/latest/closing parenthesis. The forces can be modeled as in harmonic springs described by the Leonard-Jones potential. Energy in simple harmonic motion. http://cnx.org/content/m58362/latest/cnx_15_02_Leonard-Jones closing parenthesis. Shows that such potentials are asymmetrical in that the potential energy increases more steeply when the molecules get closer to each other than when they get farther away. Thus, at a given kinetic energy, the distance moved is greater when neighbors move away from each other than when they move toward each other. The result is that increased kinetic energy, increased temperature, increases the average distance between molecules, the substance expands. For most substances under ordinary conditions, it is an excellent approximation that there is no preferred direction, that is, the solid is isotropic, and an increase in temperature increases the solid's size by a certain fraction in each dimension. Therefore, if the solid is free to expand or contract, its proportions stay the same, only its overall size changes. A. Linear thermal expansion. According to experiments, the dependence of thermal expansion on temperature, substance, and original length is summarized in the equation dl over dt equals alpha L 1.1, where delta L is the change in length L, delta T is the change in temperature, and alpha is the coefficient of linear expansion, a material property that varies slightly with temperature. As alpha is nearly constant and also very small, for practical purposes, we use the linear approximation. Delta L equals alpha L delta T 1.2. Table 1.2 lists representative values of the coefficient of linear expansion. As noted earlier, delta T is the same whether it is expressed in units of degrees Celsius or kelvins. Thus, alpha may have units of 1 over degree Celsius, or 1 over K with the same value in either case. Approximating alpha as a constant is quite accurate for small changes in temperature and sufficient for most practical purposes, even for large changes in temperature. We examine this approximation more closely in the next example. Table 1.2. Material. Coefficient of linear expansion, alpha, 1 over degree Celsius. Coefficient of volume expansion, beta, 1 over degree Celsius. 1. Solids. Aluminum. 25 multiplied by 10 to the power of negative 6. 75 multiplied by 10 to the power of negative 6. Brass. 19 multiplied by 10 to the power of negative 6. 56 multiplied by 10 to the power of negative 6. Copper. 17 multiplied by 10 to the power of negative 6. 51 multiplied by 10 to the power of negative 6. Gold. 14 multiplied by 10 to the power of negative 6. 42 multiplied by 10 to the power of negative 6. Iron or steel. 12 multiplied by 10 to the power of negative 6. 35 multiplied by 10 to the power of negative 6. Invar, nickel iron alloy. 0.9 multiplied by 10 to the power of negative 6. 2.7 multiplied by 10 to the power of negative 6. Lead. 29 multiplied by 10 to the power of negative 6. 87 multiplied by 10 to the power of negative 6. Silver. 18 multiplied by 10 to the power of negative 6. 54 multiplied by 10 to the power of negative 6. Glass, ordinary. 9 multiplied by 10 to the power of negative 6. 27 multiplied by 10 to the power of negative 6. Glass, Pyrex. 3 multiplied by 10 to the power of negative 6. 9 multiplied by 10 to the power of negative 6. Quartz. 0.4 multiplied by 10 to the power of negative 6. 1 multiplied by 10 to the power of negative 6. Concrete, brick. Approximately 12 multiplied by 10 to the power of negative 6. Approximately 36 multiplied by 10 to the power of negative 6. Marble, average. 2.5 multiplied by 10 to the power of negative 6. 7.5 multiplied by 10 to the power of negative 6. 2. Liquids. Material. Coefficient of volume expansion, beta, 1, over degrees Celsius. Ether. 1650 multiplied by 10 to the power of negative 6. Ethyl alcohol. 1100 multiplied by 10 to the power of negative 6. Gasoline. 950 multiplied by 10 to the power of negative 6. Glycerin. 500 multiplied by 10 to the power of negative 6. Mercury. 180 multiplied by 10 to the power of negative 6. Water. 210 multiplied by 10 to the power of negative 6. 3. Gases. Air and most other gases at atmospheric pressure. 3400 multiplied by 10 to the power of negative 6. Table 1.2, Thermal expansion coefficients. Thermal expansion is exploited in the bimetallic strip, figure 1.6. This device can be used as a thermometer if the curving strip is attached to a pointer on a scale. It can also be used to automatically close or open a switch at a certain temperature, as in older or analog thermostats. Figure 1.6. A. T0. B. T is greater than T0. The curvature of a bimetallic strip depends on temperature. A. The strip is straight at the starting temperature, where its two components have the same length. B. At a higher temperature, this strip bends to the right, because the metal on the left has expanded more than the metal on the right. At a lower temperature, the strip would bend to the left. Example 1.2. Calculating linear thermal expansion. The main span of San Francisco's Golden Gate Bridge is 1,275 meters long at its coldest. The bridge is exposed to temperatures ranging from -15 degrees Celsius to 40 degrees Celsius. What is its change in length between these temperatures? Assume that the bridge is made entirely of steel. Strategy. Use the equation for linear thermal expansion, delta L, equals alpha L delta T to calculate the change in length, delta L. use the coefficient of linear expansion alpha for steel from table 1.2, and note that the change in temperature delta T is 55 degrees Celsius. Solution. Substitute all of the known values into the equation to solve for delta L. Delta L equals alpha L delta T equals, open parenthesis, 12 multiplied by 10 to the power of negative 6 over degrees Celsius, closed parenthesis, multiplied by, open parenthesis, 1275 meter, closed parenthesis, multiplied by, open parenthesis, 55 degrees Celsius, closed parenthesis, equals 0.84 meter. Significance. Although not large compared with the length of the bridge, this change in length is observable. It is generally spread over many expansion joints so that the expansion at each joint is small. 1.3.1 Thermal expansion in 2 and 3 dimensions. Unconstrained objects expand in all dimensions, as illustrated in Figure 1.7. That is, their areas and volumes, as well as their lengths, increase with temperature. Because the proportions stay the same, holes and container volumes also get larger with temperature. If you cut a hole in a metal plate, the remaining material will expand exactly as it would if the piece you removed were still in place. The piece would get bigger, so the hole must get bigger too. A. Thermal expansion in 2 dimensions. For small temperature changes, the change in area delta A is given by delta A equals 2 alpha delta T 1.3. Where delta A is the change in area A, delta T is the change in temperature, and alpha is the coefficient of linear expansion which varies slightly with temperature. The derivation of this equation is analogous to that of the more important equation for 3 dimensions, below. Figure 1.7. In general, objects expand in all directions as temperature increases. In these drawings, the original boundaries of the objects are shown with solid lines, and the expanded boundaries with dashed lines. A. Area increases because both length and width increase. The area of a circular plug also increases. B. If the plug is removed, the hole it leaves becomes larger with increasing temperature, just as if the expanding plug were still in place. C. Volume also increases, because all 3 dimensions increase. B. Thermal expansion in 3 dimensions. The relationship between volume and temperature, dV over dt, is given by dV over dt equals beta the fifth delta T, where beta is the coefficient of volume expansion. As you can show in exercise 1.60, beta equals 3 alpha. This equation is usually written as delta 5 equals beta the fifth delta T 1.4. Note that the values of beta in table 1.2 are equal to 3 alpha except for rounding. Volume expansion is defined for liquids, but linear and area expansion are not, as a liquid's changes in linear dimensions and area depend on the shape of its container. Thus, table 1.2 shows liquids' values of beta but not alpha. In general, objects expand with increasing temperature. Water is the most important exception to this rule. Water does expand with increasing temperature, its density decreases, at temperatures greater than 4 degrees Celsius, 40 degrees Fahrenheit. However, it is densest at positive 4 degrees Celsius and expands with decreasing temperature between positive 4 degrees Celsius and 0 degrees Celsius, 40 degrees Fahrenheit to 32 degrees Fahrenheit, as shown in Figure 1.8. A striking effect of this phenomenon is the freezing of water in a pond. When water near the surface cools down to 4 degrees Celsius, it is denser than the remaining water and thus sinks to the bottom. This turnover leaves a layer of warmer water near the surface, which is then cooled. However, if the temperature in the surface layer drops below 4 degrees Celsius, that water is less dense than the water below, and thus stays near the top. As a result, the pond surface can freeze over. The layer of ice insulates the liquid water below it from low air temperatures. Fish and other aquatic life can survive in 4 degrees Celsius water beneath ice, due to this unusual characteristic of water. Figure 1.8. Density of fresh water. Temperature, degrees Celsius. Density, gram per centimeter cubed. Figure 1.8. This curve shows the density of water as a function of temperature. Note that the thermal expansion at low temperatures is very small. The maximum density at 4 degrees Celsius is only 0.0075% greater than the density at 2 degrees Celsius, and 0.012% greater than that at 0 degrees Celsius. The decrease of density below 4 degrees Celsius occurs because the liquid water approaches the solid crystal form of ice, which contains more empty space than the liquid. Example 1.3. Calculating thermal expansion. Suppose your 60.0-L, 15.9 gal steel gasoline tank is full of gas that is cool because it has just been pumped from an underground reservoir. Now, both the tank and the gasoline have a temperature of 15.0 degrees Celsius. How much gasoline has spilled by the time they warm to 35.0 degrees Celsius? Strategy. The tank and gasoline increase in volume, but the gasoline increases more, so the amount spilled is the difference in their volume changes. We can use the equation for volume expansion to calculate the change in volume of the gasoline and of the tank. The gasoline tank can be treated as solid steel. Solution. 1. Use the equation for volume expansion to calculate the increase in volume of the steel tank. Delta 5S equals beta S Vs delta T. 2. The increase in volume of the gasoline is given by this equation. Delta 5 gas equals beta gas V gas delta T. 3. Find the difference in volume to determine the amount spilled as V spill equals delta 5 gas minus delta 5S. Alternatively, we can combine these three equations into a single equation. Note that the original volumes are equal. V spill equals open parenthesis beta gas minus beta S closed parenthesis V delta T equals open bracket open parenthesis 950 minus 35 closed parenthesis multiplied by 10 to the power of negative 6 over degrees Celsius closed bracket multiplied by open parenthesis 60.0 L closed parenthesis multiplied by open parenthesis 20.0 degrees Celsius, closed parenthesis, equals 1.10 L. Significance. This amount is significant, particularly for a 60.0 L tank. The effect is so striking because the gasoline and steel expand quickly. The rate of change in thermal properties is discussed later in this chapter. If you try to cap the tank tightly to prevent overflow, you will find that it leaks anyway, either around the cap or by bursting the tank. Tightly constricting the expanding gas is equivalent to compressing it, and both liquids and solids resist compression with extremely large forces. To avoid rupturing rigid containers, these containers have air gaps, which allow them to expand and contract without stressing them. 1.1. Check your understanding. Does a given reading on a gasoline gauge indicate more gasoline in cold weather or in hot weather, or does the temperature not matter? 1.3.2. Thermal stress. If you change the temperature of an object while preventing it from expanding or contracting, the object is subjected to stress that is compressive if the object would expand in the absence of constraint and tensile if it would contract. This stress resulting from temperature changes is known as thermal stress. It can be quite large and can cause damage. To avoid this stress, engineers may design components so they can expand and contract freely. For instance, in highways, gaps are deliberately left between blocks to prevent thermal stress from developing. When no gaps can be left, engineers must consider thermal stress in their designs. Thus, the reinforcing rods in concrete are made of steel because steel's coefficient of linear expansion is nearly equal to that of concrete. To calculate the thermal stress in a rod whose ends are both fixed rigidly, we can think of the stress as developing in two steps. First, let the ends be free to expand, or contract, and find the expansion, or contraction. Second, find the stress necessary to compress, or extend, the rod to its original length by the methods you studied in static equilibrium and elasticity. http://cnx.org/content/m58339/latest/closing parenthesis. On static equilibrium and elasticity. In other words, the delta L of the thermal expansion equals the delta L of the elastic distortion, except that the signs are opposite. Example 1.4. Calculating thermal stress. Concrete blocks are laid out next to each other on a highway without any space between them, so they cannot expand. The construction crew did the work on a winter day when the temperature was 5 degrees Celsius. Find the stress in the blocks on a hot summer day when the temperature is 38 degrees Celsius. The compressive Young's modulus of concrete is Y equals 20 multiplied by 10 to the power of 9 Newton per meter squared. Strategy. According to the chapter on static equilibrium and elasticity, the stress F over A is given by F over A equals Y delta L over L0, where Y is the Young's modulus of the material, concrete, in this case. In thermal expansion, delta L equals alpha L0 delta T. We combine these two equations by noting that the two delta L's are equal, as stated above. Because we are not given L0 or A, we can obtain a numerical answer only if they both cancel out. Solution. We substitute the thermal expansion equation into the elasticity equation to get F over A equals Y alpha L0 delta T over L0 equals Y alpha delta T. And as we hoped, L0 has cancelled, and A appears only in F over A, the notation for the quantity we are calculating. Now we need only insert the numbers. F over A equals, open parenthesis, 20 multiplied by 10 to the power of 9 Newton per meter squared, closed parenthesis, multiplied by, open parenthesis, 12 multiplied by 10 to the power of -6 over degrees Celsius, closed parenthesis, multiplied by, open parenthesis, 38 degrees Celsius, minus 5 degrees Celsius, closed parenthesis, equals 7.9, multiplied by 10 to the power of 6 Newton per meter squared. Significance. The ultimate compressive strength of concrete is 20, multiplied by 10 to the power of 6 Newton per meter squared, so the blocks are unlikely to break. However, the ultimate shear strength of concrete is only 2, multiplied by 10 to the power of 6 Newton per meter squared, so some might chip off. 1.2. Check your understanding. Two objects A and B have the same dimensions and are constrained identically. A is made of a material with a higher thermal expansion coefficient than B. If the objects are heated identically, will A feel a greater stress than B?